Let's practice using L'Hopital's rule on some of the 0 over 0 indeterminate form limits. So first, let's start with the limit where x is approaching 0 for the function 1 minus cosine x over x. We'll check to make sure that it does follow that indeterminate form, 0 over 0, which it does. Now we can apply L'Hopital's rule. We'll take the derivative of the top function and the derivative of the bottom function. That will leave us with a new version of the limit, sine x over 1, where x is approaching 0. We can do direct substitution here, and we're pretty happy with the results from this L'Hopital rule because we see a constant in the denominator. That constant means there's no way we're going to get a 0 over 0 indeterminate form again. Plugging 0 into our numerator, we get sine of 0, which finishes off our limit, having a value of 0. Taking a look at our next one, we'll check to make sure that we have an indeterminate form for sine pi x over ln x, and we do. We have a 0 over 0 indeterminate form, so we'll apply L'Hopital's rule, differentiating the numerator function and the denominator function. Our limit now looks like pi cosine pi x divided by 1 over x, where x is allowed to approach 1. Direct substitution simplifies to give us the limiting value of negative pi. We got two more examples. Looking at the limit where x approaches infinity for the function e raised to the power of 1 over x, subtract 1, all divided by 1 over x. We first need to make sure that we are looking at a limit that follows the indeterminate form 0 over 0, and we are. So we apply L'Hopital's rule, differentiating the numerator and denominator, then simplifying our expression. Notice that the derivative on top and the derivative on bottom share a factor of negative x to the negative 2. That simplifies, leaving us with just the limit where x goes to infinity for the function e to the 1 over x. That ends up turning into e to the 0, which is equal to 1. So the limiting value for that function is 1 when x approaches infinity. Last one here. We need to first check that the limit of sine x minus x divided by x squared when x goes to 0 is in the form 0 over 0. It is. So we apply L'Hopital's rule, derivative of top and bottom, simplify. We have cosine x minus 1 on top, 2x on bottom. If we plug 0 in here, we get indeterminate form again. And we're allowed to apply L'Hopital's rule multiple times. This is a case where we need to. We applied L'Hopital's rule, and the result was still an indeterminate form. But if we apply it again, which we can because we're in that form, take the derivative of top and bottom, now we have a constant on the bottom, which we're happy with because, again, that means we're not going to have a 0 in the denominator. So a 0 over 0 is just not possible. Plugging 0 into our numerator, we do get negative sine of 0 divided by 2, and since sine at 0 is 0, the whole limiting value is equal to 0. We can also apply L'Hopital's rule in the infinity over infinity case. So just like indeterminate forms 0 over 0, we can have indeterminate forms infinity over infinity. So in this example, we're going to look at a limit which does have this indeterminate form. Notice that our limit has x approaching 0 from the right. The 0 with a superscript plus sign tells us that we're approaching 0 from the right, and that is just a property of the functions that we're looking at. ln x, the natural log function, has a domain restriction where x is not allowed to be 0 or smaller. And so we can't actually evaluate our function left of 0, which is why we're only approaching 0 from the right and not from both sides. First thing we need to do is check that we do truly have an indeterminate form. And we do. ln of 0 is negative infinity cotangent x. When x is 0 also gives us an infinite value, so we're looking at infinity over infinity. We apply L'Hopital's rule, differentiating the top function and the bottom function separately. We get 1 over x in the numerator and negative cosecant squared x in the denominator. Now, this form can be manipulated very easily So we're going to do a little bit of scratch work here and drop the numerator's denominator down to match with the negative cosecant squared. So instead of having 1 over x up top, we're just going to leave the 1 up top and let that x drop down to join the other denominator. Then we're going to rewrite cosecant squared as sine squared x. And the reason for this is because we had a negative x times cosecant squared x, and when x goes to 0, those two functions are going in vastly different places. When x goes to 0, the negative x function goes to 0, but when x goes to 0, cosecant squared x goes to infinity. And we're not quite sure who would win in that fight. Would the 0 win or the infinity win? So instead, we separate them by rewriting our expression to have sine squared in our numerator and the minus x in the denominator. This will put us back into an indeterminate form of 0 over 0 so that we can apply L'Hopital a second time. When we apply L'Hopital the second time, we do get a constant in the denominator. Notice that if we had tried to apply L'Hopital a second time before doing our scratch work, we would have actually exacerbated the situation. Taking the derivative of 1 over x would not reduce that down to a constant. And taking the derivative of negative cosecant squared x, well, that's going to require a chain rule, and cosecant x is going to stay as a factor in those derivatives because of the chain rule. So we had to do the scratch work so that we could rewrite our limit, producing an indeterminate form of 0 over 0, and then applying L'Hopital for a second time so that we could get that constant in the denominator and eliminate any possibility for another indeterminate form to occur. Now we can do direct substitution, and we see that the limit is equal to 0.